Welcome back, secondary educators. Let's talk a little bit about parallel lines and perpendicular lines. Let's talk a little bit about this idea that two lines that are parallel must have the same slope. Let's deal with that. Um, if we're talking with smaller children, younger children, less sophisticated children, we would argue that these two lines that are parallel, L1 and L2, that these lines have the same slope because they point in the same direction. And slope talks about how you point in a particular direction. With slightly more sophisticated students, we can use transformational language. We can argue that L1 is the image of L2 after a translation down. And we can argue that after a translation, slope doesn't change. Uh, it's not too hard to see. There's an over and an up. There's the delta y and delta x. And none of those change, neither of those change, just because we translated in a particular direction. Doesn't matter that we translated down. We could have translated to the right to get from L2 to L1. We could have translated on some off direction kind of a thing. It doesn't matter. The delta x is still what it is. The delta y is still what it is. There's been no rotation. There's been no dilation. And even if there was, we're fine. Depending, but because it's a translation, there's no rotation, there's no reflection. The slope remains the same after a translation. So we can talk with older students in a more sophisticated way using language they're familiar with. So parallel lines have the same slope. It's fairly straightforward to establish that, whether you're doing it with younger children or you're doing it with older children. The perpendicular argument is a little bit tougher. With smaller children, we can do this by talking about some specific examples and generalizing. With older children, again, we can use the language of transformations. If these two lines are perpendicular, then they meet at a right angle. These lines happen to pass through the origin. In every situation, no matter where L1 and L2 are on the grid, you can translate them so that their intersection point is the origin. And remember, translations preserve the delta y and the delta x, preserve slope. So we can translate any scenario to the scenario that's on the screen right now. Then what do we know? We know that if we take a particular point, x, y, on line 1, well, how do we get its image on line 2? That's a right angle, so L2 is the image of L1 after a 90-degree rotation centered at the origin. Well, we know that 90-degree rotations send xy to negative yx. So if the slope of L1 is y over x, the slope of L2 is y over x. And then what do we know? We know that the slope of L1 times the slope of L2 is negative 1, and that holds for all perpendicular lines. It is based on the notion of transformations in the coordinate plane that young people, 8th graders, do. 8th graders talk about transformations in the coordinate plane. The high school geometry course de-emphasizes the coordinate plane, but the middle school courses emphasize the coordinate plane. And so you can use this idea to drive home with young people that the slopes of perpendicular lines really do multiply to negative 1. This is where you get the idea of opposite reciprocal from. So that establishes the results using something that 8th graders have in their toolbox, and I hope you now do also.